Alright, so we are going to go to the fun part after the balancing equation stuff, electromotive force or EMF. Well, we know that water flows only spontaneously one way, right? Similarly, electrons only spontaneously flow one way in a redox reaction, from the higher to lower potential energy or from anode to cathode. That is the direction of the electron flow always if it is spontaneous. If you have to flow the electrons the other direction, then it is not a spontaneous reaction. You may have to provide energy to do that, right? So usually you have anode which has a high potential energy and cathode which has a low potential energy. So just like water, because of the high position, this top of the waterfall has a high potential energy and bottom, because of the lower position, low potential energy. Similarly, from anode to cathode, electrons also flow. So this potential difference between the anode and cathode in a cell is called the electromotive force or EMF. And we call it also cell potential because it is the potential of the cell, right? That potential difference. And potential of the cell or cell EMF is usually designated as E cell, E with a subscript cell. And the units are usually measured in volts, and here is the conversion in case, if you are calculating that from theoretical values. 1 volt is joules per coulombs. Remember coulombs? Coulombs is the unit where you measure the electrical charge, right? So if you have to calculate this voltage of the cell, this is how you calculate. Otherwise, you measure it usually in units of volts using a voltmeter. Now, this table just gives you few of the reactions and their reduction potential. Now in the table, when you see, usually we express the cell potential as reduction potentials, not the oxidation potential. Even though at oxidation the reaction might be reversed, we usually show only them as reduction potentials. Now why do we call it standard reduction potentials? When the cell operate with standard conditions and the potentials are measured against a standard electrode, which is the standard hydrogen electrode. You have a bigger table in appendix E, I think, which kind of combines a lot more reactions and giving you the standard reduction potentials, but this is from their chapter itself, table 20.1. So as I said, the standard reduction potential, why we call them, because those values are referenced to a standard hydrogen electrode. That SHE stands for a standard hydrogen electrode, SHE. In a standard hydrogen electrode, by definition, the reduction potential is 0 volt. So this is the schematic of a standard hydrogen electrode. Here you have a thin wire of platinum that is used as the electrode. It is immersed into a 1 molar solution of H plus, and it is also in contact with hydrogen gas at 1 atm, 1 atmospheric pressure. Okay, so this is the setup. Now what happens is, when this is acting as a cathode, yes, reduction occurs at cathode, right? Red cat. So when this SHE, standard hydrogen electrode acting as a cathode, what happens is, from the solution you have H plus ions which are hydrated and existing as H3O plus ions. They will accept an electron from a platinum atom and become an H atom, and 2 of the H atoms will combine together form H2 gas. So that is the reduction reaction which occurs at the cathode. As you can see, when H plus is gaining electron, so that is the reduction reaction, right, at the cathode. So at the anode, it is the opposite reaction where you have an H2 molecule separating into H plus. So H2 separating into H plus means there is a loss of electrons from H to H plus. So that is the oxidation reaction which occurs at the anode. So standard hydrogen electrode, depending on which is the other side, it can act either as anode or cathode, and the potential against this is measured and tabulated as standard reduction potentials. So the cell potential at standard conditions, once again when we say standard conditions, remember that standard conditions is 298 Kelvin temperature and when the reactants are at 1 molar concentration. That is what is usually called as standard conditions. Let's say like hydrogen gas, if one of the reactant is in the gaseous form, then they have to be on 1 atm partial pressure. So, but normally most of the cells uses aqueous reactants. So we can say reactants at 1 molar and 298 Kelvin. And the cell potential can be calculated through this equation. So E0 cell is the cell potential at the 0 represents the standard conditions. Okay, E of the cell means potential of the cell at any time. It may not be the standard condition. When you see that 0 notation there, that means it is a standard condition. So E0 of the cell is calculated as E0 reduction of the cathode minus E0 reduction potential of the anode. Remember, both are written as reduction because we tabulate standard reduction potentials, right, for cathode and anode. That is what this reduction means. But cathode comes first minus anode. That's what we usually use for calculating E0 of the cell. So this cell we have seen before, the zinc copper system. The oxidation of the cell is, if you look at the oxidation reaction, what is the oxidation reaction in this cell? Loss of electron. Which reaction is that? Look at this one. Zinc becoming zinc 2 plus and 2 electrons, right? That is the oxidation reaction. Now if you look into your table 20.1 in page number 857. What do you see for that reaction? What is the potential? Is it there on this table? Otherwise we may have to go for the, it is there, negative 0.76. You see that? Okay. So that is what is written as these numbers comes from the table. Okay. You don't have to calculate this number as such. They come from the table. Now for the other reaction, the reduction reaction, which is copper 2 plus gaining 2 electrons and becoming copper, let's find out that one also from the table. It is the same as positive 0.34. Okay, so these are the two numbers, and then remember your equation is E reduction of the cathode minus E reduction of the anode, right? So reduction occurs at the cathode. So reduction reactions potentials come first and minus, that is reduction reaction was the copper one, right? So that potential first minus anode reduction potential, which is negative 0.76. So negative becomes positive, and totally you have E of the cell, which is 1.10 volt. So this equation can be used to calculate E0 of the cell, or if you know E0 of the cell and one of the reduction potentials, you can calculate the other. You know the drill, right? Whatever, if you have two information, or if you just have the cell reaction, you can look it up from the table and you can calculate whatever is missing also. So I guess we will be doing a couple of practice problems on that. So 20.5 and 20.6. 20.5 is in page number 858. So that one is calculating E0 reduction from E0 of the cell. So if you look into the sample exercise, voltaic cell reaction is given, zinc, the same cell we looked at, and E0 of the cell is 1.10 volt. Given that the standard reduction potential of zinc to zinc zinc 2 plus 2 is negative 0.76. Calculate the reduction. Even though we know the number, we are just looking at how you do that. It's just substituting what you know and then rearranging the equation. No much big deal in there, right? So 1.10 is E0 of the cell, and cathode is what we are looking for. And so one thing you need to know there is, if it is given just as the, remember everything is given as the reduction potential. So you need to identify which one is the anode reduction potential, which one is the cathode reduction potential, right? How do we figure that out? By looking at what is going on. Where is the loss of electron, where is the gain of electron, right? Remember the oil rig. Oxidation is loss of electrons, reduction is gain of electrons, and then remember oxidation always occurs at anode, reduction always occurs at cathode. That is where I remember the two friends. Who were the two friends? An ox and a red cat. That is making it more complex. I don't know, it really helps me to remember such things. Anode at oxidation and reduction at cathode, anox and red cat. Whichever way you guys remember, I have no objection as long as you remember things. Okay, so put the numbers in its place and we have the answer 0.34. Let's do the practice exercise. So a voltaic cell is based on half reactions, indium plus becoming indium 3 plus and 2 electrons, and then Br2 liquid gaining 2 electrons and becoming 2 Br minus. We know the standard EMF for the cell, so we have to calculate the reduction reaction of indium 3 plus to indium plus. That's what we are looking at. Okay, so first we have to figure out which one is the cathode reaction, which one is the anode reaction. Indium plus becoming indium 3 plus and 2 electrons. Is that oxidation or reduction? That is, yes. Plus becoming 3 plus means it is losing electrons. So if it is oxidation, which electrode it will occur? The anode, right? So that one is the anode reaction, and therefore the other one has to be the cathode reaction. Okay, so now we can write out our equation. So E0 of the cell is given to us as 1.46, and well, how do we write that? E0 cell is E0 reduction of cathode minus E0 reduction of anode, right? So 1.46 is E0 reduction of cathode. We don't know that, so we have to find from the table. 20.1, does it have the indium reaction? Oh, I'm sorry, the cathode one is Br2 reaction, right? So Br2 one yes, it has Br2 plus 2E giving 2 Br minus is 1.06. So this part becomes 1.06 and we don't know this one, right? So we will leave that as reduction of anode. So rearrange the equation. 1.46 minus 1.06 will be, what is it? 0.40 is negative E0 of anode. So E0 of anode should be negative 40, right? Oh, negative 0.40 volt. Is that the answer? Yeah. So it's just, you just identify which reaction is it asking. whether it is anode or cathode, then only you can place it in its place in the equation, right? That's all. So the next one is calculating E cell from E reduction potentials. So using the standard reduction potential listed in table 20.1, calculate the standard EMF of the voltaic cell described in sample exercise 20.4, which is based on the reaction. Okay, we have the reaction. So Cr2O7 2 minus plus 14H plus 6I giving 2Cr3 plus 3I2 plus 7H2O. Okay, so first we have to identify which is the anode reaction, which is the cathode reaction. Then only we can put the correct potentials in its place. Correct? So Cr2O7 2 minus plus 14H plus 6 electron. Okay, you are right. You have to write it as balanced equations. Wow. So if you take Cr2O7 2 minus becoming 2Cr plus, you will see that you need 14H plus and 6 electrons here and 7H2O to balance. So that becomes your what equation? The cathode half reaction, because Cr2, which is oxidation state, is 0, but it is becoming Cr3 plus, right? It is gaining electrons. Look at that, 6 electrons is added to that half reaction. So wherever it is gaining electrons, that is the reduction reaction, and reduction happens at cathode. So that is the cathode reaction. Therefore the other one, I minus becoming I2 plus 6 electrons, that has to be, that is losing electrons, I minus is losing electrons, that has to be the oxidation reaction. Now we can find out what are the values, corresponding values. Cr2O7 reaction, do we have that on the table? Yes, we have Cr2O7 plus 14H plus 6 electron. That equation is on the table, which has a reduction potential of 1.33. So that is the cathode one. So that minus I minus becoming I2. Oh, I have I2 plus 2 electron becoming 2I minus. That is given as 0.54 positive. So cathode minus anode becomes 1.33 minus 0.54. So 0.79 volt is the E0 of the cell. So shall we do the practice? Okay. So practice exercise reads as 2 aluminum plus 3 I2 gives 2 Al3 plus and 6 I minus. So 2 aluminum becoming 2 Al3 plus is one reaction, and 3 I2 becoming 6 I minus is the other one. Which one is oxidation, which one is reduction? Aluminum from 0 it is becoming 3 plus, so that is losing electrons. So this is oxidation, so this is going to be the anode reaction, right? So the other one is reduction, and this is the cathode reaction. Once you identify that, all you need is that table, right? So E0 of the cell is cathode value, which we just found, I think. The same number, 0.54. So 0.54 minus, what is the Al becoming Al3 plus? Negative 1.66. So this is minus 1.66. So this will be plus 1.66, right?
No matter what the coefficient values are in the equation, you don't multiply through by the corresponding ones?
No, we don't. For the E0 it doesn't matter. But later in this chapter, when we connect EMF with the equilibrium constant, that time the mole ratios comes into the picture. But as long as it is just the EMF, it doesn't matter how many moles of it is reacting. It doesn't depend upon the amount.
Same voltage no matter what you do.
Exactly. So E0 of the cell is going to be, number of these two numbers added together, what do we get? 2 point something? 2.2. Okay? All right. So continuation on cell potentials. So the greater the difference between the two, the greater the voltage of the cell. That is, the greater the difference between the E0 cathode and E0 anode, greater the difference, greater the voltage of the cell. Well, of course, that is understood, right? Because E0 cell is calculated as cathode minus anode. So if they are, far apart, that difference is going to be great, which is the cell potential. Now one more thing is, the more positive E0 reduction value identifies the cathode. So sometimes, just by looking at the reaction. So far what we were doing was, we were looking at the reactions and we were identifying which one is the oxidation, which one is the reduction, and then we know oxidation always happens at anode and reduction happens at cathode. That is how we identified. Another way of identifying anode cathode reactions are, among the two values, you find out the two half reactions and just look for the values from the table. Among the two values, the more positive will be the E0 reduction of the cathode. Okay, cathode will have the more positive value. So if you look at the previous example we just did, so this was copper, cathode reaction was copper 2 plus becoming gaining 2 electrons, and the potential was, reduction potential was 0.34. What am I misspeaking so much? And the anode was negative 0.76. So even though you didn't know that was cathode or anode, just by looking at those numbers, you can say which one is cathode and anode, right? Because now you know that the more positive number is the cathode number. Okay. So, determining half reactions at electrodes and calculating cell EMF. Okay, so a voltaic cell is based on the following two standard half reactions. Cadmium 2 plus gaining 2 electrons and becoming cadmium, and zinc 2 plus gaining 2 electrons and becoming zinc. Okay, this is why this point was talked about, because if both are given as gaining electrons, you will be wondering, hello, how is that possible? Both are reduction happening, both have reactions, right? So you have to figure out by looking at the value which one is the cathode reaction and which one is the anode reaction. So we need appendix E. I don't think those numbers are in your chapter itself. So if you go to appendix E, which is in page number 1117, CD2 plus 2 electrons. Let's figure that out. Where is it? Do we have it here? Yes. CD2 plus 2 electrons. Do you see the number negative 0.403? It's on the left side. Okay, so this one is given kind of alphabetical order, guys. So CD is after B, C, that's CD. So negative 0.403, and then Sn plus 2 electrons, that is S, almost to the bottom of the the right half. Sn plus 2 electron is negative 0.136. So both are negative, but which one is more negative or which one is more positive? That's what you are going to look for. The numbers are negative 0.403 and negative 0.136. What? Yes. So by looking at those numbers, we know that the more positive one is the Sn reaction, right? So that is going to be the cathode reaction. So we will use that number in place of cathode, and the anode reaction is the other one. So cathode minus anode becomes negative 0.136 minus becomes plus. So again you will end up with E of the cell, which is a positive value. Okay, so let us do the practice. Voltaic cell is based on a CO2 plus CO half cell and an AgCl Ag half cell. So again we have to figure out, we have two questions. What is the half reaction occurs at each anode, and then what is the standard cell potential? So CO2 plus becoming CO. Oops. So okay, let's first get the numbers for both of them. It's only asking for what half reaction occurs at the anode. So first we have to figure out the numbers and which one is the anode and cathode numbers. So CO2 plus and CO, what is the number, guys? Negative 0.277. So let's write that down. So CO2 plus is negative.
Does it matter that it's in reverse order?
Well, right now I'm just writing down the numbers. Later we will focus on what order it has to come. Okay? Which order you will write the reaction. What was the number? Negative 0.277. And the other one is AgCl Ag. Positive 222. Okay, so those are the two numbers. So looking at these two numbers, we can immediately say which one is the cathode reaction, right? This is going to be the cathode reaction. So this one has to be the anode reaction, correct? Now anode, what happens? No. Anode, what type of reaction happens? What happens at anode? Oxidation, right? And oxidation is loss of electrons. So you have to write this in a way which shows as loss of electrons. How can you write that? Cobalt becoming CO2 plus and 2 electrons. So cobalt is losing electrons. So the oxidation reaction has to be this, and oxidation happens at anode. Therefore that is the reaction at anode. That is your philosophy. Okay? So let us, just for the sake of it, what will be the cathode reaction? Can we write the cathode reaction? Okay. Cathode, what is happening at cathode? Well, let's just look at how that reacts. It's not simple Ag, there is Cl also. So let's just look at in appendix E how that reaction is written. AgCl plus 1 electron giving you Ag and Cl minus, right? Oops. So AgCl plus 1 electron I'm sorry, it is Ag solid, otherwise you don't need the electron, right? And Cl minus. So here you can clearly see it is gaining an electron, right? So this must be the reduction reaction. So you have to think in that way. Oxidation is loss of electrons. So when I show the reaction, it should show I am losing electrons. If it is asking you to write the anode reaction. If it's asking you to write the cathode reaction, remember reduction occurs at cathode, so my reaction should be written as I am gaining electrons. Okay, now the second part of the question, which is what is the E0 of the cell? Since we have the numbers, it's easy. Cathode minus anode, right? So cathode is 0.222 minus anode, which is minus 0.277. So that is going to be a plus. Add those two numbers and you should have your cell potential, which is 0.499. Yeah. So far we are good? So, oxidizing and reducing agents. When we talk about the strength of oxidizing and reducing agents, the more positive standard reduction value for a half reaction, the greater the tendency for it to be reduced and therefore to oxidize another species. Remember, the species which gets reduced, we call it the oxidizing agent, right? And the species that gets oxidized, we call it the reducing agent. So keep track of those words in there, okay? Because when you read both oxidation and reduction, it is easy to get confused. And therefore, the strongest oxidizers, remember we just said in the previous slide, E0 reduction at the cathode has the high positive value. And what happens at cathode? Reduction, or things are getting reduced. So the things are getting reduced, they are called oxidizers. So the strongest oxidizers have the most positive reduction potentials. Make sense when you connect all those things? And similarly the opposite, the strongest reducers have the most negative reduction potentials. So if you look into that table 20.1 in your book one more time, you will see the most positive number is given for F2 plus 2 electrons becoming 2F minus. That is on the top of the table, right? So fluorine is the most, the strongest oxidizing agent. So at the bottom what you see, that should be the strongest reducing agent. So the lithium which you see in the bottom with the negative 3.05 value is going to be the strongest reducing agent.
So which one make a lithium fluoride battery?
Yeah.
But they don't usually make lithium fluoride batteries. A lot of them are lead or they're nickel cadmium.
Well, I think those two combinations are dangerously strong.
Because it seems like even with like a lead battery, you have to put it in series because you can't get 12 volt difference. You can only get, it's about 2. Like even like nickel cadmium, you can only get like 2 volts of difference, which means you have to hook up 6 different
Yeah.
cells just to get a 12 volt battery.
Yeah. I guess this one, more than just looking at how much volt you can produce, I guess the consideration here will be how safe you can make it. Fluorine compounds, usually the sodium fluoride and those things are very, very dangerous to handle because of the strong oxidizing power of fluorine. I mean, for us to handle, like you can imagine the nitric acid, when it gets in touch with your skin, it oxidizes your skin and immediately your skin burns and you get the yellow thing. The fluorine, it's really harmful. And fluorine, it's not only just does harm to your skin, it has the ability of getting absorbed through your skin to the blood. There are some chemicals which does that, and that increases your dangerous level. I mean, if something gets directly to the blood, then what else you want? Just circulate all through the body, and such a strong oxidizer, it just goes and kills all the tissues where the blood goes. I mean, I'm not saying, in the battery form, if you are doing it, you will be directly touching the chemicals in the battery. But I would think the cover of that battery, that protective, the shell or the case we talk about, that should be maybe a little more tougher than what we normally see on the other batteries.
It'd just be hard to get safe.
Yes.
So like a disposable battery then?
What? Cardboard? Yeah.
Treat cardboard, if you would make a battery that's strong enough to reinforce
exactly. If you are making a battery like that, yeah, you really have to think about. Well, that's for the future scientists to work on, right? What material you can use for making a case for such a battery?
Don't get him started. Probably
He will start on that.
will.
He's already working on a battery case.
He needs something to power his ship.
Well, at least this slide is clear for us for the purposes of understanding strongest oxidizing agents and strongest reducing agents, right? Wonderful.
My friend who's a textile engineer, she might actually be able to help you with the
So now we are on to connecting. Well, before connecting, let's just look at the free energy. So free energy delta G for a redox reaction can be found by using the equation negative NFE. The negative sign is there. N stands for the number of moles of electrons transferred. So here, Tyler, your previous question, does it matter the equation is multiplied by a coefficient? Yes, when it comes to free energy, and later when we connect that to equilibrium constant, it will matter. So N stands for the number of moles. F is a constant called Faraday's constant, which has a value of 96,485 coulombs per mole, and E stands for what? What is E? The cell potential, right? So this is connecting free energy to cell potential. This equation connects free energy to cell potential. Now, we were talking about the cell operating under standard conditions. So if the cell is operating under standard conditions, we can rewrite the equation as, instead of just free energy, it is the free energy of formation is equal to negative NF and EMF of the cell also under the standard conditions, right? Now this is an important equation because recall from last chapter, section 19.7, that we learned this equation. Free energy of formation is negative RT ln K. So we have two equations for free energy of formation. Now if you are connecting both of the equations, that will enable us to calculate equilibrium constant and free energy from the cell potential. Well, yeah, you can isolate K. That's what basic idea is. So these two equations, they relate the standard EMF E0 to the equilibrium constant of the reaction. I guess we will have a problem to do, definitely. 20.10. So 2010 is which page? Page number 864, determining delta G0 and K. Okay. So the question is, sample exercise, the question is, use the standard reduction potentials listed in table 20.1 to calculate the standard free energy change delta G0 and the equilibrium constant K. And we have just the reaction given, 4 silver plus O2 plus 4H plus giving 4 Ag plus and 2 H2O. Well, there is a second question. Suppose the reaction in part A was written as 2 Ag plus half O2. If we have the coefficients changed, what are the values of E0, delta G and K when the reaction is written this way? Okay, so this is going to show us when we change the mole coefficients, delta G and K will also change. So let's focus on first step, that is from table 20.1 we need the values for both half reactions. So looking at the reaction, what are our half reactions? First we need to come up with that, right? And then only we will know which one is reduction, which one is oxidation, or from the numbers, the more positive one is at the cathode, the less positive one is at the anode. Whichever way you are going for, you have to identify that first. Then only you can calculate the E0 of the cell, right? That is our first goal. So if you see how they have solved it, So they have written both half reactions, that is O2 plus 4H plus 4 electrons be giving 2H2O, and oxidation is 4Ag becoming 4Ag plus and 4 electrons. So Ag becoming Ag plus is your oxidation reaction. Silver is losing electrons, right? So that is your oxidation reaction, and from the table you have the value 0.80, and reduction reaction is the other one with the value 1.23. So when you calculate the E0, cathode reaction 1.23 minus anode reaction 0.80 gives you 0.43, which is your E0. Now substitute that into delta G0 is minus NF E0. That is the equation which connects delta G0 and E0. So F is a constant, N is the molar coefficient of the number of electron transfer, and the equation that is 4, right? So we need to use 4 in place of N. So when you just substitute the numbers and do the multiplication, you end up with negative 1.7 into 10 to the power 5 joules per mole, or negative 170 kilojoules per mole. So you have the delta G0. Now use the second equation which connects delta G0 to equilibrium constant K. So delta G0 is minus RT ln K. Again substitute the values. R is the universal gas constant, 8.314 joules per Kelvin mole, and T is the temperature, and it says it is standard reduction potentials or this reaction. Oh well, they specifically say the 298 Kelvin in the question itself. Otherwise, from the word standard, you can imagine or you can assume that the temperature is going to be 298 Kelvin, right? That's what the temperature for standard conditions. So when you substitute all the numbers and isolate ln K, ln K is 69, therefore K is 9 into 10 to the power 29. So that was our first question. Okay, calculating E0, delta G0 and K. Now the second question is, if you write the reaction with half coefficients for everything, would it change the value? So now your reduction and oxidation reaction has half coefficients, but we know that from our previous example, for the calculation of E0 it doesn't matter, right? When we calculated the E0, it doesn't matter what coefficients you have. So E0 is going to be still the same, your positive 0.43 volt, but in delta G0, remember the N comes into the play. So here N is 2, not 4. Therefore you get exactly half of what you had in the previous one, because 4 by 2 is 2, right? It's reducing by half, and therefore K is also going to reduce by half. Make sense? Okay, now let's do our and again, if you read the comment, E0 is an intensive quantity, so multiplying a chemical reaction by a certain factor will not affect the value of E0. So intensive quantities doesn't matter, the quantity doesn't matter, it's the value itself, right? But the other stuffs, they are extensive quantities, that means the amount matters when you calculate, that is free energy and equilibrium.
So in other words, they're saying that the half one, that was just showing us. The first step is the correct answer.
Exactly. As it is given, that's what, it's that half one was just to illustrate E0 wouldn't change, but delta G0 and K will change. Let's do the practice exercise. Let me get a new screen. Oh. So, for the reaction, 3Ni2 plus 2 CrOH3 plus 10 OH minus giving 3Ni plus 2 CrO4 2 minus plus 8 H2O. What is the value of N? Use the data in appendix E to calculate delta G0 and then calculate K. So first we need the oxidation and reduction half reactions. Of course, Ni2 plus becoming Ni. Which reaction will be that? It is gaining electrons, right? How many electrons it has to gain? Look at the charges. 3, 2 plus charges. How many positive charges on the left side? 6. Right side is all 0. So how do we balance the charge? Plus 6 electrons. Okay? Do not forget that 3. 3 in front means 3 times 2 plus. So this is our reduction half reaction. So the value of this will be our cathode value, right? So the other one, the anode reaction, let's write that also just for practicing. What is the anode reaction? 2CrOH3, 2CrOH3 solid plus 10 OH minus giving 2CrO4 2 minus 2CrO4 2 minus plus 8H2O. Okay, we have to show this as oxidation. So, left side, what is the total number of charges? 10 negative charges, right? Right side, what is the total number of charges? 2 times 2 minus 4 negative charges. So to balance, what do we need on the right side? 6 electrons. Do not forget, if one side, if you have used 6 electrons, then it has to balance on the other side, right? So those are your two half reactions, and we know this is reduction, which is the cathode reaction, this is oxidation, so this is the anode reaction. Now you are ready to look into the table and figure out what are the values for these two reactions. So we need appendix E. Nickel reaction. Nickel, where is it? Nickel 2 plus 2 electrons giving nickel solid is negative 0.28. So if you are calculating E0, we want the cathode one first, negative 0.28 minus CrO4, Cr something, let's check the Cr section. We have CrO4 minus plus 4H2O plus 3 electrons giving CrOH3 plus 5OH minus. Everyone see that reaction? Okay, what is the value? Negative 0.13. So negative 0.13 will become, what is it? We should have a negative value for E0. 0.14. Oh. Ah, I hate that. Don't tell me it's all gone. Yes. Deep breath. Okay, I'm not going to write everything again. I'll just do the E0 because you have written down everything. So E0 cell is negative point, give me the numbers one more time, 28 plus 0.13, and what did we get? Okay, 8 minus 3, yeah. So this is our E0 of the cell, right? Now we can calculate delta G0. What is the equation? Delta G0 is minus N F E0, right? So you just have to substitute the numbers. Negative, what is the molar coefficient of electrons in our reactions? 6. So negative 6 multiplied by Faraday constant is 98,000 something. Oh, 96,485. 96,485. And E0 is, we just calculated, negative 0.15. So we should have a positive value because negative sign and negative sign will go away. We are multiplying everything. What do we get? What is it? 86,836.5. We should be having the answer in what? Joule. What are the units? What?
Right now it's in joules.
Okay, this is right now in joules. So if you want to write that in kilojoules, well, you can leave it as in joules because for next step you have to have that in joules.
The book just gives it to you in kilojoules.
Okay, okay.
It's 87 kilojoules.
Okay, yeah, that makes sense. If you want to show only 2 significant digits, then you can round that as 87 kilojoules. But joules is perfectly fine because in the next step we are using joules, right? Then only the units will cancel away. So that is delta G0. Now we need K, so we have to use the equation delta G0 is negative RT ln K, right? So we have to substitute the numbers again. Negative 8.314. If you are using the joule value, remember everything will cancel perfectly. T is 298 ln K. So isolate ln K. Ln K will be whatever this value, which is right here, 86,836.5 divided by negative the product of these two numbers. What do we get? If somebody did that.
Negative
2477.
24.572.
We'll just leave it at 2477. Okay. And when you solve that, what do you get? ln K.
Solve for K or solve for L?
Just for ln K.
Negative 35.45.
35.4505. Okay. Now go ahead and do the K. K is e to the power that number. Negative 35.05. What do we get? Do we get the answer in the book?
Yes.
6.0 times 10 to the power negative 16? 16 or 6? What is it? 16. Okay. So, we can do this problem, right? So, all we need is the reaction. So, first you have to write this as the half reaction. And remember, since for delta G0 we need the N, it is important that you go balance the half reactions. Just to make sure what is the molar coefficient of the electrons, right? So first you do that and then take the half reactions, take the reduction potentials. Either you can look at the reaction and figure out which one is oxidation, which one is reduction, therefore anode or cathode. I think I'm more comfortable doing that way because I was trained that way. But you can look at the both numbers, and the more positive one is going to be the cathode one, whichever way you find it easy, because both are theoretically right. So it will be the same. And then calculate the E0 of the cell. Once you have the E0, delta G0, from that negative NFE, Faraday's constant will be given to you in the problem. You don't have to by heart Faraday's constant. And once you have delta G0, you can substitute for that for the next equation, negative RT ln K. Okay? All right. What honey? ln,
The X top.
how did I get the ln T alone on the left side?
No, treat the other side. Hit the second LN button and then punch in your quantity.
Oh, you are asking on the calculator. Oh,
Yeah.
okay. I'm sorry.
Thinking more.
That's what you asked, right?
Yeah,
Okay.
Did you get it?
yeah.
Okay. So we will look into one more equation. Again, recall from last chapter that we had another equation, just free energy, not free energy of formation. Free energy is free energy of formation plus RT ln Q. What is Q? What? What is Q? We have seen Q in chapter 15 when we learned equilibrium constants. The big Q, yeah, reaction coefficient. Remember, the equilibrium constant K is concentration of the reactants over products at equilibrium, right? Q is the reaction quotient, which is concentration of the reactants over products at any time. That is the Q there, okay? So delta G is delta G0 from RT ln Q, and now we had seen an equation before for delta G, right? Delta G is negative NFE, so substitute that in place of delta G, so we get, and substitute negative NFE0 for delta G0, so we get this equation. Negative NFE is negative NFE0 plus RT ln Q. Don't copy it down because that is not your final equation. We are going to simplify that much further to a form which you can actually remember and easy to use.
Plus, we didn't really figure out how to do this cell reaction potential is not standard as the non-standard.
Non-standard one, that is after this equation we will be able to do this. So far we were doing only assuming that everything is under standard conditions, right? But that's not true. Every time cells cannot be under standard conditions. So that's what we are developing. So now the previous equation you had, if you go divide both sides by negative NF, then we get this equation which is called the Nernst equation. So E is E0 minus RT over NF ln Q. So R is a constant, T is a constant, F is a constant, E0 we can calculate using the standard reduction potentials from the table. So the only variable is going to be there, E and Q. Now Nernst equation, this is how you derive it, but normally when you use it, you don't use the natural logarithms. Not that in the equation you have ln Q, right? But we usually don't use it ln Q when you do the Nernst equation. So you will convert that into base 10 log, and converting from natural log to base 10 log is multiply by 2.303, right? So that is what is showing there in the next one. So your equation becomes E0 minus 2.303 RT over NF, and now this becomes log Q. Now look at this big thing. This big thing you have written down. You can further simplify this. 2.303 is a number. R is a constant, T is a constant, F is a constant. So if you substitute all those numbers in its place and solve, you get a much simpler equation. Okay, so the value of all that stuff, all the numbers you do, this is what you get. So the equation becomes very simple, E0 minus 0.0592 over N and log Q. So N will be that molar coefficient of the electrons. E0 you can calculate from the reduction potentials, and Q, well, if you have Q then you can calculate E, if you have E then you can calculate Q, whatever you are asking for you can do it.
Now this is all at 20 Kelvin.
This is assuming that it all happens at 298 Kelvin. That's what it says, at room temperature. Okay, but the reactions are not at equilibrium. It doesn't have to be. That is why we are using Q. You can calculate this at any time. Remember, Q is products over reactants products over reactant concentration at any time, right? not exactly at equilibrium. So just from this previous equation, we can see that the cell EMF depends only on concentrations. The Q is concentration based, right? Q is from the concentration of products over reactants. So cell EMF depends only on concentrations. Then we can create a cell which has the same substance as both electrodes. So far we were looking at all cells with anode has a different half reaction and cathode has a different half reaction, or we need two different things in anode and cathode. But this Nernst equation allows us to create cells with same substances but at different concentration. So the standard EMF will be 0 because under standard conditions both are same half reactions, so one cancels the other, so the standard EMF will be 0. But remember that the cell is operated under non-standard conditions, because in the standard condition you want the concentration of the reactants 1 molar. If you are not keeping that point, that is if you are keeping them in two different concentrations, then by definition your cell is not operating under standard condition, right? So your cell itself is operating under a different condition or non-standard condition. So as long as we keep those concentrations difference, you will get a cell EMF, or it will not be 0. So here is an example, the nickel concentration cell. So when you have this type of cells, that is a cell which use same chemical species in both anode and cathode, or same half reaction for anode and cathode, but you get a potential because of their concentration difference, those types of cells are called concentration cells. Here is an example. In the anode half cell, you have Ni2 plus nickel ions at 1 into 10 to the power negative 3 molar concentration, and on the cathode half cell you have a concentrated one which is 1 molar. Now in the anode oxidation, what happens is from the nickel anode, a nickel atom will lose 2 electrons and become Ni2 plus and get into the solution. So slowly this number here, slowly the concentration of Ni2 plus is going to increase, right? So the electron which is lost will pass through here, come over here. When this electrode becomes negative, a nickel 2 plus from the solution will accept those 2 electrons and get attached to the nickel electrode. So slowly here the concentration of Ni2 plus is going to come down. After a while, note that both compartments have exactly the same concentration. At this point we will say the cell is dead. The cell will not, because since the concentrations are exactly the same, nobody can move. I mean, no oxidation happening, so no loss of electrons, no flow of electrons, means we will say the cell is dead.
Dump water to one side.
If you dilute, again go ahead and dilute this one. Yes, once again it will start, this nickel will lose 2 electrons, come into the solution, and those 2 electrons will pass through. Here it will come and again it does the same, the cycle will repeat. As long as the concentrations are kept different, you will definitely get a cell potential. But once the concentration of anode and cathode become exactly equal, cell becomes dead. This is how the concentration cells will work. Make sense? Okay. Where is my, okay. Applications. Why don't we start at that in the next class? Because I think applications, there are a lot of applications we are going to look at.
So is that all the battery stuff?
Yes, all the battery stuff, different types of batteries, fuel cells.
Catalyzer,
Yep. And then we will look into even corrosion also. So that's what is left. What? You talked about what?
cathodic protection. Like we had like a whole class on cathodic protection.
Oh, okay. Well, I guess in your program it has.
We're